Good evening, everyone. Geotechnical Engineering Part A, Soil Mechanics. So let's solve an interesting problem in soil consolidation. So in this problem, if we have like a foundation with a 6 feet width times 40 feet length and handling a concentrated load of 300 kips standing over saturated consolidated clay soil with the over consolidation ratio OCR equal to 3. We want to calculate the primary consolidation settlement of the clay soil after the footing is poured and loaded. So we are looking for settlement, consolidation settlement in the middle of this clay layer. So if the specification of soil are provided, the thickness of the clay soil is provided like 15 feet. We want to know what is the consolidation settlement at halfway through of the clay soil, and these are the specification of clay soil. Gamma saturate is 125 pound per feet cubed. Initial uh, void ratio is equal to 0.7 and CS swell coefficient is 0.02. Let's see the effect of a stress distribution. So if we have our foundation and if you move as you move farther down farther, the effect of a stress is reducing because the platform is going to be higher and higher. We can have it like a similarity between the a foundation with the light distribution. As the light moves from the torch, the cross-sectional area get larger and larger. The same energy through the larger area has a lesser effect. So if we define the intensity of light by small e equal to capital E over area, and definitely A2 in denominator is increasing, so the intensity of light is decreasing at the larger area as you move farther from the light. So the same concept apply to geotechnical engineering. And an idea of a stress distribution in soil is like the effect of exactly like the same effect of if you have both torch and there is a uh, part which both torch shed lights on that um, yellowish area, and we can call that that's the intensified light. So let's back to our foundation. So at the very top we have dimension of B times L, and definitely sigma is just force over the area. And when you move with down with the height of C like 7.5 at the mid layer of 15 feet clay, that's a delta sigma P over B plus Z times L plus Z. And that's if you want to get delta sigma from sigma, that says it's just I times sigma, and we call that influence coefficient, which is a number definitely less than 1. So the effect of a stress when you move farther down, deeper in soil, that's a number less than sigma, less than 1. We call that number like capital I, and that's influence coefficient. So, for example, if in a case of sigma is B times L, as we move deeper in the soil, intensity of load is reduced. So P is equal, the same load is equal to sigma stress times the area, and it should be equal to delta sigma times in a very common condition in foundation is the uh, slope of 2 vertical, 1 horizontal. So if you move like by a height of z, at each side you are increasing a z over 2. That's why we call it b plus z, and like on the other dimension is l plus z. So delta sigma is definitely this one, and that's influence coefficient. And if we just translate it into our own problem to see what is the effect of delta sigma in our soil, so one can say if our foundation is B times L, let's replace the numeric value in our problem. So that's P over BL, a 300 kilopounds over the area of 6 times 40, and delta sigma is definitely the same load over the z for each part. So a 6 plus 7.5. So as we talk about it. So as you move farther down with the height of z over 2 or 7 plus 7.5 over 2 added to each side of our foundation and at the depths of z. So if the dimension is 6 times 40 at the surface, you are going to be 6 plus 7.5 times 40 plus 7.5 at the height of z. And definitely delta sigma is 467.8 36 pound square inches. You have to compare this number with the effect of sigma, which is definitely higher that number. So if you divided 300 kilopounds by the area, it just gives you 1250 psi, which you can see how it just decreases to almost 500 when you dive deeper to the soil. And then if you want to calculate the consolidation settlement, now we had just the delta sigma effect at the depths of uh, z, which is 7.5. Let's calculate sigma prime at that depth. So if gamma saturate is 125 and the water surface stands at the top here, so sigma prime is definitely 125 minus gamma w, which is 62.4 in USCS customary times the z, which is 7.5. And if you do the math, it just gives you a 469.5 psi. So if you want to know in which consolidation category we stand, if you review the consolidation conditions, we have like three cases. Like if we have delta sigma versus the logarithm scale of p or sigma prime, we have two zones like over consolidated zone and normal consolidation. We If both fits are stand before pre-consolidation load or pressure, we call that like over consolidated, and like case 2 is when both fits are in normal consolidation scenarios a condition, and the last case is when one feet of your pressure is stands at the over consolidated, and if you jump the other feet, it just gives you in the normal consolidation. So that's case 3. In our case, so we have OCR is which is the ratio of PC pre-consolidation uh, pressure, consolidation pressure over P naught, which is we already calculated the effect of delta sigma at the depths of z is equal to almost 465.8 pound square inches, and we also calculated sigma prime 0 at the depths of z, and that gives us this numeric number. And we have over consolidation ratio, which is 3 provided in problem statement. If we multiply these two, so we have like our number, which is here, P naught times over consolidation ratio, we can get what PC is. And then as soon as we get the PC, we can compare the P naught plus delta P is equal to this part. Let's make it a bit cleaner. Plus the delta P, and if you add them up together, that's 937.336 psi. And if you compare them with PC, you can easily see the both fits are smaller than P naught plus delta P is smaller than PC. And in our in the consolidation categories, we stand in the very first part. So P naught plus delta P is smaller than PC. So if that's the case, we have to use this formula. Consolidation settlement is CSH naught over 1 plus E naught times logarithm scale of P naught plus delta P over P naught. And so if that's the case, and by P naught is sigma prime Ceph and delta P is delta sigma. So P stands for sigma, and that's sigma C. Mm. So if both fits are standing in the over consolidation part, so we can easily use the coefficient of that part. Some books show it by CR, and that's identical to CS. So this is in normal consolidation part. We have a compression coefficient. In over consolidation part, if you see it by like CR, that stands for recompression coefficient, or CS stands for swell index. They are both the same, but the different terminology. So we are definitely, both fits are in before PC, so we are in over consolidation part. So we have to use this coefficient CSH naught over 1 plus e times logarithm. So for CS, we have like 0.02, which is provided in the data of problem. E naught is provided to be 7. We already know the total height of clay layer is 15 feet. P naught or sigma prime 0, we already calculate this part. And this part we also calculated, like that's 937.3. And if you replace that, it just gives you an a this much settlement in the center of clay soil, and if you multiply it by 12 inches, it just gives you 0.3657. So consolidation settlement at the middle of our clay layer is equal to consolidation settlement is equal to 0.636 inches at the center of our clay soil. Thank you. We'll solve more.